Go ahead and talk about perpetual motion machines. Perpetual motion machines is any device that violates one of the laws of thermodynamics. A perpetual motion machine of the first kind violates the first law, and a perpetual motion machine of the second kind violates the second law. So a reversible process, a process that can be reversed without leaving any trace to the surroundings, is called a reversible process. This is possible only when the net heat and work exchange between the system and the surroundings is zero. Reversible processes are idealizations. They do not occur in nature. A reversible process is any process that is not reversible, and these are the ones that usually do occur in nature. So, factors that cause a process to be irreversible is friction, for example, or unrestrained expansion of a gas, heat transfer through a finite temperature difference, or the mixing of two different substances. All of these cannot be undone unless some work is put back into the system. So, why are these reversible processes of interest if they don't actually occur? Well, these processes serve as what we would say are idealized models. They're useful because you can compare the actual processes to the idealized processes to provide a theoretical limit to how well the process can occur. Reversible processes deliver the most work to work-producing devices and consume the least work for work-consuming devices. So, for example, a pump. The more efficient a pump is, the less work the pump consumes to produce the pressure change. For a turbine that produces work, the more reversible the turbine is, the closer to reversible process the turbine is, the more work it will produce for the same change in pressure of the steam. They are easy to analyze, and since the system passes through a series of equilibrium states during a reversible process. So these idealized processes are pretty easy to analyze. The reversible and irreversible processes. An internally reversible process is a process in which no irreversibilities occur within the boundaries of the system during the process. An external reversible process is a process in which no reversibilities occur outside the system boundaries during the process. And totally reversible is a process that does not involve any irreversibilities within the system or the surroundings. Let's look at an example. Consider the transfer of heat to two identical systems that are undergoing a constant pressure phase change process. Here we have our phase change occurring at 20 degrees Celsius, and I have a thermal energy reservoir at a temperature that is slightly larger, but it's like basically the same temperature as it is inside, and I'm transferring heat to the system. That would be something that's called total reversible. Internal reversible would be if I have a thermal energy reservoir that has a temperature higher than the inner temperature that allows me to transfer heat. So in this example, both A and B are internal reversible since both takes place isothermally and pass through the same equilibrium states. A is external reversible since the heat transfer takes place through an infinitesimal temperature difference. And B is external reversible since it involves heat transfer through a finite temperature difference. Let's look at a Carnot cycle. A cycle composed of 4 reversible processes is a Carnot cycle. 2 of them are isothermal, and 2 of them are adiabatic. The processes can be executed in closed or steady flow devices. So let's look at the first process. This would be process 1 to 2. Reversible, isothermal, heat addition. to the working fluid in a piston cylinder device that does some boundary work. So I have an energy source, and I'm supplying heat to my system. And it causes the piston to move from this point to that point in such a way that it is expanding in order for the heat transfer to the system to not cause a temperature change. Process 2 to 3 would be reversible adiabatic expansion, during which the system does work as the working fluid temperature decreases from TH to TL. So from process 2 to 3, I have expansion. It's adiabatic, meaning no heat transfer, and as it expands, the temperature goes from TH down to TL. Next is process 3 to 4. The system is brought into contact with the heat reservoir at TL, and a reversible isothermal heat exchange takes place while the work of compression is done to the system. So again, as I'm compressing from point 3 to point 4, the tendency is for the temperature to want to increase, but I'm rejecting the heat to the environment so that during that compression, the temperature remains constant. And then process 4 to 1, the last process, is reversible adiabatic compression, during which the temperature of the working fluid increases from TL to TH. So I compress, no heat transfer takes place, it's adiabatic, and the temperature increases from TL to TH. This is a Carnot cycle as described by Sadi Carnot. This is what the Carnot cycle looks like on a PV diagram. So pressure on the y-axis, volume on the x-axis. The area under the curve represents the boundary work for a quasi-equilibrium process. So the area under 1 to 2 to 3 is work done by the gas during the expansion part of the cycle. 3 to 4 to 1 is the work done on the gas during the compression part of the cycle. The area enclosed by the cycle path, this highlighted area in red, represents the net work done during the whole cycle. A reversed Carnot heat engine cycle is a Carnot refrigeration cycle. So all processes involved are reversed. The direction of any heat and work interactions are reversed. Heat and amount of QL is absorbed from the low temperature reservoir. Heat and amount of QH is rejected to the high temperature reservoir. And a work input of W net in is required for the cycle to operate. So let's go over some of the Carnot principles, a little overview. The Kelvin-Planck and the Clausius statements of the second law of thermodynamics place limits on the operation of cyclic devices. The Kelvin-Planck statement says a heat engine cannot operate by exchanging heat with a single reservoir, meaning I can't convert all heat into work. The Clausius inequality says that a refrigerator cannot operate without a net work input from an external source. Two valuable conclusions can be drawn from these statements pertaining to the thermal efficiency of reversible and irreversible engines. These conclusions are called the Carnot principles. The efficiency, here's Carnot principle 1. The efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. So I have a hot source TH here, a cold sink, TL here, and heat engines that are all operating between the same two reservoirs. The irreversible efficiency of a heat engine operating between the two reservoirs has to be less than the reversible heat engine efficiency. And the reversible heat engine efficiency is limited by the temperature of the hot reservoir and the cold reservoir. So there's a certain limit to how high the efficiency can be, and it cannot be 100%, because I cannot convert all the heat coming from this into work. I have to reject some heat for it to happen. And the efficiencies of all, the second principle saying is, the efficiencies of all reversible heat engines operating between the same two reservoirs are the same. So here's an example of a proof. We have here a high temperature reservoir, a low temperature reservoir, a irreversible heat engine taking in heat QH, rejecting heat QL, and producing a net amount of irreversible work. Here is a reversible heat engine taking in heat, rejecting heat, and producing a certain amount of reversible work. This reversible work would be higher than that work. Or if I have a refrigerator, I would be absorbing heat, putting work into the system to move heat from the low temperature to the high temperature. So a reversible and an irreversible engine operating between the same two reservoirs. The reversible heat engine is then reversed to run as a refrigerator. So basically, this efficiency will be less than that efficiency.